We're going to talk about the free particle, and in talking about this we're going to come across a couple concepts. First, the concept of a wave packet, and also the concept of a Fourier transform, which we're going to find is very similar to the Fourier series we've done before. A free particle is a particle that's not under the influence of any potential. So that would be our definition. So what that basically means for us is our potential is equal to 0 for all x. Of course, this is an idealization. No system is truly isolated, but in many cases the external forces on a particle are so weak that we can neglect them. An example would be in electron scattering experiments. We use an electron beam, beam of electrons. This is technically under the influence of gravity, but since this force is pretty weak, these electrons may be treated as free particles. So where do we start with this? Well, we start by taking our time-independent Schrodinger equation, so right here, and we're going to, again, cross out this term because the potential is 0, which gives us the same equation we had inside the infinite square well. And usually the way we do it is we take that and we isolate the second derivative of the wave function, and we find that it equals negative constant times the wave function, where again this constant is this k from right over here. And so we've talked about this a couple different ways, but the solution to an equation like this is some kind of oscillating wave-like solution. We've used sines and cosines in the past, and what's going to actually be more advantageous in this case is to use the complex exponential, which again is just the same thing really. It's just a combination of sines and cosines. A really key thing here though is that there aren't any boundary conditions. Okay, we don't have the end of a well or something like that to quantize our system, so the free particle can carry any energy. This k constant can be anything that we want it to be, and so that's going to have some important ramifications. So let's get to know this state a little bit better. So I'm just going to use the positive one, and so we've already talked about this a little bit. This is the momentum eigenstate, and so let's look at this. Well, if I was to write this out, it would be a cosine kx plus I sine kx. All right, now whenever you have cosine k of x, right, so that k is, we call that the wave number technically, and if you write that out, you would write that out as 2 pi over the wavelength. All right, and so let's take this quantity here, p equals h bar times k. Well, what you get is h bar times k, and so if we write out that in terms of this thing we have over here, 2 pi over wavelength, okay, so I'll keep writing this. H bar is, of course, h over 2 pi. You get this here, and so what we really are getting here is that because of the way we've expressed momentum as being the Planck's constant over a wavelength, then one way we can express our momentum is being h bar times k. All right, and so we're calling this here in terms of k, but k is just really an h bar away from being a momentum. And so we sometimes, we wrote this way here, I P0x divided by h bar to get the k in there. And so this is a state that has a definite k value, which means it has a definite momentum. Now another way to kind of think about that is our k vector or our k constant, if you look at it, looks like this here. And so if I just sort of take that, I can square both sides. K squared equals 2me over h bar squared, and if I solve that for e, I get this thing over here, which of course if we think about our energy, this is our kinetic energy only because there is no potential, as being p squared over 2m, then again our p comes out to be h bar times k. So sometimes you'll see books that'll talk about this function this way. In fact, I think that's the way Moore did it. Sometimes, like Griffiths, will write it in terms of k, but really since the p and the k are only off by a constant, when we talk about k, we're really talking about the momentum. All right, so everything that k does that we talk about, momentum will do too, and so that's why we talk about this as being the momentum eigenstate. Now the next thing we would do oftentimes with our solutions is we would write them out as a function of time. And so we have now, this is the function, wave function with x, and so if I want to write out my whole solution here as x comma t, what do I do? Well, I write a, the actual solution, a to the ikx, and then I write in here e to the negative I energy. Now my energy now is h bar squared k squared over 2m, and this is times t divided by h bar. And then I can do the same thing for the other piece. So e to the negative I kx, and then e. Now since it's negative, it's going to be still positive k there, and so this will be the same, negative h bar squared k squared over 2m t divided by h bar. And so you can see here I've sort of cleaned this up a little bit. You can take this, and so this is e to the I kx, and then this second piece, when you write it out, will be negative I. So one of the h bars cancels, k squared over 2m times t, and the same thing over here. And so we write it like this way. And when you have these two exponentials multiplied by each other like this here, you can just sort of add up. You make one exponential with adding up the two pieces inside there. And what's nice is both of them have an I and a k in them. Okay, the energy one has like 2 k's, k squared, but you can pull that out and write the function this way here. Now we've seen this function before in physics, and basically whenever you have a function, you can write x minus constant times t. All right, that represents something that's propagating in the positive direction. And then the same idea here, x plus h, some constant times t, gives us something propagating in the negative direction. So we can interpret these two solutions, this one propagating in the positive direction, this one propagating in the negative direction. Now you've probably talked about this in physics. There's lots of ways to kind of think about this. For me, the easiest way to think about this is sort of thinking about mathematical descriptions. Okay, and so here's a shape. This is actually a Gaussian function, and the Gaussian function, you can graph it as e to the negative x squared over 2 sigma squared. That's the official form of a Gaussian. And then now, if you remember, if you graph something in mathematics and you make your function f of x, you make it fx minus d. Okay, what does that do? Well, that basically takes your function that used to be centered at the origin and now centers it at x is equal to d. All right, and so I've got that x minus d in there. And then sort of the next step, what you can do is just call your d to be velocity times time. So this distance d is increasing as velocity times time increases. And so if I get this function of x minus v sub t, what that really means is now this shape, this Gaussian, is moving to the right with some velocity. All right, and that's exactly what our functions for back over here are doing. So this one, again, is in the sort of shape of an x minus v sub t, and this one's in the shape of an x plus v sub t. And so this one would be propagating in the positive direction, this one's propagating in the negative direction. All right, now the good thing is we've talked about this function a little bit before in class and homeworks and things, the momentum wave function. So let's answer this question here. So choose all the following statements that are correct about the wave function for a free particle. Okay, so the first one says that the stationary state wave function for a free particle, e to the I kx, has a well-defined magnitude of momentum. The stationary state wave function of a free particle, e to the I kx, has an infinite uncertainty in position, and the stationary state wave function, e to the I kx, of a free particle is normalizable. So go ahead and think about this one, and we'll talk about it. Okay, so hopefully you agree 1 and 2 are correct. So we just talked about how this wave function has got a definitely set k value, and so because of that, it's going to have a definite set momentum. So the magnitude of our momentum would be h bar times k. The stationary state wave function of a free particle has an infinite uncertainty in position, right? So we sort of talked about this. So if I take my psi of x squared, I would get e star, so e to the negative I kx times e to the I kx, that's an x, and you just get 1 out of there. And so if I was to plot this, all right, so if I was to plot my psi squared versus x, I get some constant function. Sorry, it's not very constant, but basically the area under the curve, first of all, is infinite, and it's equally likely to be anywhere. So it's equally likely to be anywhere, then it has an infinite uncertainty in position, and then the stationary state wave function is not normalizable. It's got infinite area under this curve, and so at least in the way that we've talked about normalization so far, this is not normalizable. And then just real quickly, we can sort of think about the uncertainty principle. So sigma x, sigma p. So what we're saying here is that my uncertainty momentum is 0, and so the only way my uncertainty can equal some constant number, okay, which is what it should do in terms of this, is if my uncertainty in position is infinite. And so we've talked about that in a homework, but just good to go over that. So what this means for us is a free particle cannot exist in a stationary state, okay, with some definite energy. So basically our free particle can never just be in the state e to the ikx. And so you can say, well, why are we doing this then? Well, what we can do is set up a linear combination of these e to the ikx solutions and have that represent a particle. And that's going to be our best way to represent a particle. And so let's look at this. So we've been dealing with sort of this function here a little bit, hopefully getting better with it. This is our wave function as a function of position and time, and we write it in terms of our energy eigenfunctions. And this is the time our time piece, our time evolution piece, and these are the CNs, again, which are sort of telling us sort of basically how much of each one of these energy eigenfunctions contributes. Well, in this new equation here, it's the same idea, except because the k is continuous. Okay, so that's the sort of tricky part. Before our energies were discrete, well, now our k is continuous. It can take up any value, and so instead of having a sum, we have a nice integral. Right, so that integral sort of replaces where the sum was. Now this is our eigenfunction, right? So the format of this thing up here was we have our energy eigenfunction, the time evolution. Well, here's our energy eigenfunction. Here's my time evolution, just like above. And then all this business here, which we're going to spend a lot of time talking about, that is basically what our Cn is. Okay, and so we're going to spend some time unpacking this to try to understand it better, but it's really just the same thing we've been doing in a continuous case. So physically, what this means is this picture that we've shown several times. Okay, so I can add up a bunch of different plane waves here to get this wave packet, is what we're going to call it, all right, that basically has some confined position to it. Okay, so all these things have sort of position everywhere, just like our e to the ikx does, but if you add up enough of the e to the ikx, you get this thing that has some sort of a more certain position, and we call this a wave packet. And this is going to be our best representation of a particle. And so the actual math behind this, again, is this thing we just sort of showed. So this is, again, this is my energy eigenfunction, this is my time evolution piece, and then this part will end up being equivalent to my Cn. And again, because it's continuous, we're integrating now instead of taking a sum. And that's really the only difference. All right, and so if we clean this thing up here a little bit, so I can pull out this factor of 1 over radical 2 pi, and then if I actually just plug in what my e to the n is, which again is h bar squared k squared over 2m. So sometimes you'll see this all written together, right? But really it's two distinct parts. It's the energy eigenfunction, so my energy eigenfunction, and then my good old time evolution piece for more. And so this function can be normalized. Okay, but in order to do that, it must include a range of k's. So there must be many k's in order to get it so that the area under the curve is finite. And we call this a wave packet. And again, it's our best description of a particle. Now, what do we need to do this? Well, just like before, what did we need? Well, we needed to find those CNs and to be able to represent our sum. And so now we're going to need to solve for this we call phi of k. Right? That was the thing that we are saying is our Cn now. We need to solve for this thing here. And the way we're going to do it, again, is very similar to how we did it before. Okay? Really the only difference is that now we're taking a sum, instead of a sum, we're taking an integral. And I know, I mean, that's, of course, makes everything much trickier, but just conceptually, it's very similar. And so this equation, okay, which is the idea of using the Fourier transform, is how we're going to do this. And we're going to see that basically the Fourier transform is extremely similar to our Fourier series. But this is our equation. So just like before, what you'll be doing is you'll be given an initial wave function, and your goal is to find this phi of k, which is our C of n's. And we'll talk about what that means a little bit. And the way you do that is by taking this Fourier's trick. Okay, if you investigate this, this is really nothing but the Fourier trick integral. Okay, and so here's how we can compare these two. So here's this this integral. So again, the phi of k is the same thing, or is very similar to my Cn. All right, and then here in this equation, this e to the negative ikx is our psi star. And so I would even maybe put psi n of star just so you can see that that's the same thing from there. And then literally that's my initial wave function. And so the one big difference there is just this constant of 1 over radical 2 pi, which just comes from the sort of normalizing this thing properly. So we've shown this picture a few times. Doesn't make it any easier, but this is our general procedure for solving one of our problems right now for a time-independent potential. So we're given our potential and our initial wave function. So the first thing is we solve our time-independent Schrodinger equation and find our energy eigenfunctions and the associated energies with each one of those. And then we write the initial wave function in terms of these energy eigenfunctions. So it's a key for us here for solving this C sub n. Once we have that, we multiply each state by the time evolution, get our time evolved, and then we can go through and answer various questions. Well, so one thing is, so if someone asks, what does the solution to the generic quantum problem mean physically? Well, this is what we mean by that. I think Griffiths had said this quote in the book, and this is the solution to the generic quantum problem. And so now we're doing this for the free particle. So our v sub x is 0, and our energy eigenfunctions are these e to the ikx's, which happen to be the momentum eigenfunctions. And so now, instead of solving for the Cn, we've got to solve for this phi of k. So once we solve for that, we can do this integral, right, and basically represent our wave function in terms of this right here. And then once we know what that phi of k is, I can then write my time-evolved wave function this way right here. And so here we can take this, and this is a way to represent our wave function at time 0, and then here we get the wave function as a function of time, and then in a similar way we can go through and calculate different things, whatever we want to find out. And so the big thing now we're introducing is this phi of k. Let's talk about this. This is sometimes referred to as the momentum space wave function. And again, I'm just going to point out that momentum and k are just off each other by one constant. And so the way this works out is if I take my phi of k squared and say plot that, okay, maybe it looks like this or something. So this is a function versus k. But the behavior of this is very similar to how our wave function that we've dealt with so far works. And so basically this curve we have here is the momentum space wave function absolute square, and so it gives us a sense of what k values we're most likely to find if we were to look and try to measure the k, which again, measuring the k is just the same thing as measuring the momentum. Okay, so for instance, it's much more likely in this picture for us to say, you can imagine measuring a k somewhere in this region right here, than maybe somewhere in this region right over here. So you get that kind of information from this. Here's what a student said last year, that this phi of k, the momentum space wave function, is showing us the spectrum of all the waves in the wave package. So maybe they meant packet, but either way sounds good to me. So using phi of k, we can say how much, again in quotes, of one particular wavelength is there in the wave package. Because again, remember our k is just our wave number, which is 2 pi divided by the wavelength. Another way to sort of think about this is, so here's our phi of k's. We're trying to say that they're similar to the CNs. And so here, some books like to do little charts like this. And so this is a chart. This is the probability on this side. And then this is the different ENs. And so basically when you talk about probability, what you're plotting is your CN absolute squared. And so you can see here that the E2 is very likely, E1 a little bit less, E4, and then E3, I think there's actually a mark there, but it's really super tiny. So maybe it's even at 0, I can't really read it. But basically, this is a way to sort of mark out, sort of what are the more likely energies. Now, this is discrete, but you could draw some sort of a function like this to sort of kind of connect the little dots there. Okay, and so even though it's not smooth like this, you can kind of imagine that it's like that. Well, that's really what phi of k is. And so here it is a graph of phi of k for some system. And again, it's just telling you, so this is the k, and so here's k equals to 0, here's k equals to 5, 10, 15, and so you can kind of go up to that point and then kind of get a feel for basically how likely that particular k value is for our particular distribution. Okay, so it's got a sort of similarities there. And then just to end off, so we're going to, in class, go through example 2.6 from page 62. And basically what they do is they start out with this initial wave function. So here's your initial wave function, psi x comma 0. And it's basically got a height of a from negative a to positive a. And it goes through and it solves for the 5k for that and tries to explain it a little bit. And so read this over and we'll talk about this in class. And so like the first question I usually ask is what value of a will normalize this wave function? Well, hopefully you can see that in this case here, if I was in this case to plot psi squared, then we'd have a box of height a squared and length 2a. Right, and so if I was to plot that, and so the total area under the curve would be a squared times length of 2a, and that would equal 1. And so if I went through then and solved for a, it would be a is equal to 1 over radical 2a.